In this chapter, we will be introducing the concept of radicals. In this lesson, we're going to be introducing entire radicals and mixed radicals. And to start, we're going to look at square roots and cube roots.
Okay, hi everybody. So now we're going to start a chapter on radicals. And to start off with, this is going to be a little bit of a longer lesson because there's a lot of little details that we want to get in order. But we're going to look at entire radicals and mixed radicals. Okay, this is our first lesson here. And we start by introducing square roots. So let's kind of zoom in on this a little bit. So square roots. We're going to talk about what a square root is. Now, there's a little bit of a clarification I want to make here because I think what's written here might give you you might be led to form the wrong conclusion here. So I just want to make sure this is clear here. So 7 times 7 is equal to 49. Okay, 7 shows up as a factor twice. So the square root of 49 is 7. Okay, now -7 times -7 is also 49. And so the intention of this is that we're going to write here -7, but I just want to be clear about this. When the square root symbol that we're going to use, okay, is going to be this guy right here. Okay, so this is the square root of 49. Now, just to be clear, there is only one answer to this, and the answer is 7. That's it. And the reason for that is because this notation right here is designed to take you from an area to a side length. Okay, so when we square something, when you do 7 times 7, that's 7 squared. Okay, there's our 49. What is this notation trying to tell us? Well, it's trying to tell us the area of a square where both the side lengths are 7. So 7 and 7, 7 times 7 is 49. The area of this square is 49. But what if we're looking for the opposite here? What if, for example, we know that the area of this thing is 49? How do I get the side length? Well, what we do here is the square root of 49, the square root of 49. Now, because this notation is related to the side lengths of a square, it's always going to be positive. So just to be clear, that's always positive. Now, there is this negative option that pops out, but this is where it pops out. If I take a variable and square it, and I'm getting 49, well, what's the opposite of squaring? Well, square rooting. But when I ask the question like this, when I tell you that I squared a number and got a positive 49, well, what was that number? Well, that number is going to be the square root of 49, but now there's a little bit of ambiguity because when I square something, if I square a positive number, I get a positive. If you square a negative number, you get a positive. So the original here could have been positive or negative square root of 49. So just to be clear, the square root of a number is always going to be positive. But if I said I squared a number and got 49, that number that you squared could have been either positive or negative. I know it's a very subtle difference, but it's an important one here. So the number 49, when it says here it has 2 square roots, okay, just to be clear, it depends on how you're asking that question there. So the positive root is going to be called the principal square root. Okay, so the square root of 49 is 7. The negative square root is called the secondary square root, okay? And we denote it like this. Now notice here that what we're doing is we're actually putting a negative in front of both of those. Now if I took this equation right here and divided both sides by a negative, well then you'd get the square root of 49 is equal to positive 7. Yeah, the negative one, I kind of have to throw that on both sides here because technically speaking, the square root of 49, okay, can never be a negative number. It can't be -7 because the square root cannot produce a negative result. Okay, unless you put a negative in front of it, like we did right here. So again, what we're saying here is correct from a certain perspective here. I just want to make sure that everything you get here is consistent. Okay, this wouldn't have made sense if we don't explain it the way I've been doing it here. So every positive number has 2 square roots, a principal square root and a secondary square root. A negative number does not have a square root in the real number system. And I really appreciate the way this was written because you can take the square root of a negative. It's just that it's not going to be a real number. And man, I wish we had a chance to talk about that. That is some really interesting math. Another time, then we'll get to that. So the square roots of a perfect square are rational numbers. So the square root of 36 is 6 and negative 6 here. So when we take 36 here and we take the square root of it, we get a nice number here. We don't get any crazy non-terminating decimals. We just get these nice numbers here. So that makes it a perfect square. If you've got a number that's not a perfect square, for example 35, then we're going to get irrational numbers. Okay, that is basically, those are your two options here. You're either going to get a rational number, which is a nice value that you've worked with kind of throughout your school career here, and then an irrational number. There's your non-terminating, non-repeating decimal. Kind of one of those two options there. All right, so cube roots. Cube root is basically related to taking or finding the volume of a cube, or a rectangular prism, if you will. You go length times width times height, but when the length, width, and height are all the same, you're going to generate the volume of a cube. So the cube root of 27 is going to be 3. Now, notice that negative 3 times negative 3 times negative 3 is negative 27. The negative pops out of this. So another square root of, now it shouldn't be another square root because this is a different number, okay? Negative 27 is a different number than positive 27, and its cube root will be negative 3. And in this case, we can say that, okay? When, in this case right here, because we've got an odd number of negatives being multiplied together, the result is negative. In the previous example, when we had two negatives multiplied together, they canceled each other out and giving a positive result, and that leads to a little bit of confusion that I'm hoping that we've established how that works here. But with a cube root, and by the way, with a 5th root, 7th root, 9th root, and so on, the negative is not a problem. If there's a negative there, the negative just pops out. So all numbers, positive and negative, have only one cube root, okay, denoted by the symbol cube root here. If it's a negative number, it's got a negative cube root, and so on. The cube root of a perfect cube is a rational number. So the cube root of 1,000 is 10. So cube root of 1,000 is 10. The cube root of negative 8 is negative 2, and that's how we write that. And just like it was before with the square root, if you're looking at a non-perfect cube, you're going to get an irrational number. You're going to get this non-terminating, non-repeating decimal. So the cube root of 49 is going to be this non-repeating, non-terminating decimal, which is kind of a neat result here. It's one of the two here. Okay, so now we're going to take a look at just some quick examples. Okay, so without using a calculator, we're going to find the roots of these questions here. So first of all, the square root of 64. Well, now I got to think, what number multiplied by itself gets me 64? So I just got to run through the numbers in my head here. I go like 5 times 5 is 25, too small. 7 times 7 is 49, we just saw that. 8 times 8, there it is. 8 times 8 is 64. So I know that the square root of 64 is going to be 8. Now notice I'm not going to put positive and negative 8 there. That's not true. And I'll show you in just a second how that works here. The square root of negative 64, well, we talked about this just a few moments ago. I cannot take the square root of a negative, so this right here has no real solution. It does have a solution, it's just what we call an imaginary and complex number, okay? There's kind of two different words for it, and we'll get into that later here, but there's no real solution here. Now over here, negative square root of 64. Now when you put a negative in front of an expression like that, bear in mind that what you're doing is you're multiplying that by a negative value. This is basically like negative 1 multiplied by the square root of 64. And that little bar across the top here is telling me that it's like a set of brackets around here. And I need to do what's inside there first. So I need to take this square root before I multiply by negative 1. I already know that the square root of 64 is going to be 8. So this is going to be negative 1 times 8, or negative 8. So just to be clear, a square root, that symbol right there, if I cover up that negative, that symbol right there can only produce a positive result. If I want the negative result, I need to include it. Okay? Now, over here, the cube root of 64. Okay, well this is probably for a lot of people here, this is a lot less obvious. Okay, cube root. So I'm looking at a number multiplied by itself. So it comes up as as a factor 3 times. So 2 times 2 times 2, that's 8. 3 times 3 times 3, it's going to be 27. 4 times 4 is 16 times 4. There's my 64. So the cube root of 64 is going to be 4. The cube root of negative 64. Now we saw this above here. What happens if that's an odd root there? The negative just pops out. The odd root has no problem at all with negatives being inside there, so it just pops out here. And again, the cube root of 64 is going to be 4. The negative out front basically acts the same way as we did over here. Remember, that's simply going to be negative 1 multiplied by the cube root of 64. We already know that the cube root of 64 is 4, and so the answer is negative 4. So really, these two expressions are the same thing. Okay. I hope that makes sense. We're going to keep doing some more examples here. Okay, now we're being asked to use the square root or the cube root symbol to evaluate the following. So here we're starting off with the cube root of 729. Now, the cube root, on most calculators here, there's going to be a symbol for it, basically up with the buttons near the top of the calculator. If you're using one of these graphing calculators, I have to go to my math menu, so press that button, and I will come down, and there's my cube root right there. So the cube root of 729. I suspect most of us don't know what that is right off the top of your heads there, and oh, there it is, the answer is 9. Here, I'm asking for the square root of 196, and most calculators actually have a square root button. It's usually associated with the square button, so second square, that brings up my square root symbol here. 196, press enter, and we get 14. So the square root of 196 is 14. Okay, we're back to the cube root again here. So I'm going to press my math button. I'm going to go down to my cube root, and now it's 512 divided by 343, so 512 divided by 343, and I want to make sure that's all underneath that radical symbol, that bar there, because remember, that bar implies a set of brackets around that. I'm going to press enter, and I'm getting a kind of a strange decimal here. Now, this question told me that I should be able to get an exact value. A decimal is not an exact value, and the reason for that is the calculator is rounding at some point here to give me this value here. As soon as you round, you're not looking at an exact answer. But based on the way this question is worded, I'm assuming that is an exact answer, so I'm going to actually use my calculator to convert that to a fraction. I'm going to press the math button, and on this calculator, the very first option is to convert to a fraction. Oh, and that gets me 8/7. Okay, so that right there is equal to 8/7. Another thing that I could have done here is I could have taken the cube root of 512 and the cube root of 343 separately. Okay, I could have done the, whoops, sorry, not that. I could have done the math. Cube root of 512 is 8. The cube root, no, I did it again. The cube root of 343 is 7. And then my answer would have been 8/7. So there's a couple of ways I could have done that. Okay, let's take a look at another question. All right, now this next question is really just asking us to plug stuff into our calculator and round it appropriately. So I want to do the square root of 45 to the nearest hundredth. So the square root of 45, 6.708. So to the nearest hundredth, 6.708. I'm going to round that up to a 1 here. And notice that I'm using the little dot over the equal sign because that's only approximately true. It's not exactly equal to 6.71. It's only approximately equal to that. I'll do a similar sort of thing here, but this time with the cube root. So my math menu down to the cube root of 85. Okay, now 4.39. When I round that to the nearest hundredth, that 9 is going to go up to the next 10, really, which is going to increase that 3 to a 4. So my answer here is going to be approximately, okay, 4.40. Okay, Okay, rounding is important here. If you make rounding errors in your work here, particularly if you've got several calculations to those errors get larger and larger and larger. So you want to make sure that you're doing that properly. Okay, so let's move on with a little bit more theory here for a second. Talk about radicals. Now, numbers like the square root of 27 and the cube root of 28 are actually examples of what we call radicals. We use the word square root and cube root. Well, the word root is usually associated with the solution to an equation. Okay, and this is, I mean, these are typically the way we solve equations here often is to find these roots. But this number right here, when it's written like this, is actually called a radical. Okay, when it's got that square root symbol here, or I should just say the root symbol there, that's a radical. And actually, that's a better word for it. And it consists of three different parts here. First of all, you've got the radical symbol, okay, which is that kind of check mark sort of thing. You've got the index there. I'll zoom in a little bit here. The index here tells you what the radical is, what kind of a root you're taking. Now, if it's a square root, you don't write it, right? If this is a square root, if that's supposed to be 2, you typically don't write it. But if it's a cube root, you put a little 3 there. Fourth root, you put a little 4 there, and so on. And then the value that you're taking that root of, okay, that's inside the radical here, that's called the radicand. Now, just so you know, and I know that you've seen this before, but just to reiterate here, notice the connection between those two. If I take a number and raise it to the 1 over n, that is the same as the nth root of that number. So just for, as by way of an example here, if I had 9 to the 1/2, whoops, that is the same as the square root of 9. And I chose this one here because, remember, if the root index is 2, like it would be here, I don't have to write it. But if it was the cube root, if I was asking you for the cube root of 8, that would be 8 to the 1/3, and then I would write that as the cube root. I would have to indicate that that's the cube root there by putting the 3 there. Okay, so anyway, that being said, let's take a look at some examples. Okay, so we're going to quickly slide through this because the question is really just identify the index and the radicand in each of the following. And that's really just a matter of location, just making sure that you recognize when you're looking at it where things are located. So the index here, that's located right there. So the index is 3. The radicand is 123. It's the part underneath the radical. Here, what's the index? Well, the index sits right here. If you don't see a number there, then that's because it's a 2. The radicand sits underneath the radical symbol, so in this case, 33. Here, now don't get thrown off by that extra number out front here. This is actually the coefficient. The index is the number that sits kind of in the little V part of the root symbol there, so it's going to be 5. The radicand is the number underneath. Don't let that number out front, again, don't let that confuse you. It's just the coefficient of the radical. Okay? Okay, now for a little bit more theory. Let's talk about what happens when you combine radicals together. So in this little section right here, we're going to use the calculator here, or we might not even use the calculator here, but we're going to talk about how these different roots here are related. So let's talk about this one. Root 25 multiplied by the square root of 16. Well, now, okay, I know that the square root of 25 is 5, and I know that the square root of 16 is 4. So I know that together this is going to equal 5 times 4 is going to equal 20. I know that 25 times 16 is 400. And yeah, I know I'm a bit of a nerd here. I know that the square root of 400 is 20. So I know that these are the same. So this is equal to root 25 times 16. So I can either take the square root of the two numbers separately and multiply them together, or I can multiply them together and then take the square root. Doesn't change anything. Okay, now let's take a look at this. Root 25 divided by root 16. Okay, well I know that root 25 is going to be 5, and I know that root 16 is going to be 4. Okay, and 5 divided by 4 is 1, oops, 0.25. 1 and a quarter, if you want to think of it like that. Well, 25 divided by 16, if I go to my calculator here and take the square root of that, so the square root, 25 divided by 16, I get 1.25. So these are equal to each other, is equal to. Okay, so doing the division between the two radicals is really the same as doing the division within the radical between those two numbers. Same thing. Now, root 25 plus root 16. Well, that's going to be 5 plus 4. That's going to be 9. 25 plus 16 is 41. The square root of 41 is not 9. This is not equal to. So that's interesting. So with multiplication, I could either put the multiplication between the two radicals, or I could put the multiplication within the radical, and I get the same answer here. Same thing with division, but addition does not work like that. Square root of 25 minus the square root of 16, that's going to be 5 minus 4, so it's 1. But 25 minus 16 is the square root of 9. Okay, and the square root of 9 is 3. Well, that's 1 and 3. Those are not equal, so this is not equal to. Okay, so multiplication and division work out pretty okay with these radicals here, but the addition and subtraction do not. So now here's just a quick summary of what we were just looking at here. The product or quotient of the roots of two numbers is equal to the root or of the product or the quotient of the two numbers. So just like we had there. So root 9 multiplied by root 4 is equal to the square root of 9 times 4. Okay, just like the square root of 100 divided by the square root of 4 is equal to the square root of 100 divided by 4. But the sum or the difference of the roots of two numbers, that is not equal to the root of the sum or difference of the numbers here, okay? Those are not the same. And this is going to be something that's going to catch people kind of over and over and over again, okay? It is very different. These are not the same. Okay. But it's such a common mistake for people to do this because they know that it works with multiplication and then they automatically assume it works with addition. Please bear in mind that it doesn't work like that. And now we'll just zoom in here on this little statement here. So in general, root A multiplied by root B is the same as root AB. Okay. As long as the numbers are greater than 0. Okay. As long as we're talking about positive values. And the square root of A divided by the square root of B is the same as the square root of A over B. Again, as long as we're dealing with numbers that are positive. And specifically, we need B to be bigger than 0. Can't divide by 0. That doesn't make any sense. It's undefined. Okay, so our question right now is asking us to write each as a single radical. Okay, so based on the rule that we've just learned here, this should be relatively straightforward. Root 8 times root 3 should be the same as root 8 times 3. And I know that 8 times 3 is 24. Okay. Root 50 divided by root 10, okay, is going to be root 50 divided by 10. And I know that 50 divided by 10 is just 5, so root 5. Over here, this one's a little bit weird because it's the square root of the square root of 100. Here, I'll zoom in a little bit there. Okay, so what do you do when something looks like that? Well, what you do is realize that when you've got that bar across there, that implies a set of parentheses. And I got to do what's inside the parentheses first here. So here's that outside square root. And now, look at that inside square root, the square root of 100. Well, the square root of 100 is 10. And so now I've got the square root of 10 divided by the square root of 2. Okay, now I've got them in a simple form that I can now combine them. So I know that the square root of 10 divided by the square root of 2 will be the square root of 10 over 2. And I know that 10 over 2 is just 5. So here's another one that turns out to be the square root of 5. So this question wants us to write the following as the product of two radicals. Okay, well, let's take a quick look at this. 77, I got to think, what numbers can I break 77 up into? Well, because it's repeated, I can tell there's an 11 in there. So it's got to be 7. this has got to be the square root of 7 times 11, which means this would be the square root of 7 multiplied by the square root of 11. 27? Well, I mean, that one's a little bit more obvious here. I know that 27 is going to be 3 times 9. And so as a result, I can split that up into root 3 multiplied by root 9. Okay. 40. Okay, well, 40 can be broken up a whole bunch of different ways. It could be 4 and 10, 8 and 5, 20 and 2. So it doesn't really matter. We just want to pick one of those. Let's do, let's do 20 and 2. So 40 will be 2 times 20. And so then I can split that up into two radicals as root 2 times root 20. 56. 56 is the same sort of thing. There's a few different ways you can get it. I think most of you are going to think 7 times 8 when you see 56. And so then I can split that up into root 7 multiplied by root 8. Okay. Notice it's really important where I stop the radical symbol. I don't want to keep drawing it, because as soon as you tuck something underneath that radical, it's inside the radical. So you got to make sure that you're being very deliberate about what you put under there and what you don't. Okay, now let's take a look at entire and mixed radicals. And this is actually what the lesson was called. It's about this right here. So root 48 is an example of an entire radical. And what we mean by that is the number, in this term here, the number is contained entirely within the radical. Whereas this next one here is a mixed radical, 3 root 5, because part of this number is underneath the radical, but part of it isn't. Part of it's a coefficient multiplied out front. Just like 4 root 6 is also a mixed radical, because part of it is underneath the radical, part of it is multiplied out front. Okay? So now, we're going to start to give you some tools here for doing some manipulation with radicals here, but we want you to see how this works here first. So we're going to use a calculator. I'm going to use a calculator here to evaluate what each of these radicals are. So first of all, root 48. So second x squared to get my square root symbol, and then 48. Okay, so let's say to the nearest hundredth, 6.93. So this is going to be approximately, to 5 decimal places. Oh, okay, that's a little bit more involved here. So 92820. So 6.92820. Here, 2 multiplied by the square root of 12. Okay, 2 multiplied by the square root of 12. Oh, look at that. It's the same number here. Okay, so, well, just easy enough to copy that over. So 6.92820. And then finally, and I know you can kind of see the other side here, it's bleeding through a little bit, but 4 root 3. 4 times the square root of 3. And look at that. It's the same thing. So it's approximately equal 6.92820. So what do I notice about all my answers? They are identical. Okay, they are absolutely identical. So now let's explore that a little bit. Why? Why would that be the case? Well, let's take a quick look at this rule again. So the square root of xy is equal to the square root of x times the square root of y. Now, what we're going to do is we're going to use that idea here to complete this little bit right here. So notice that root 48 could be written as the square root of 4 multiplied by the square root of 4 multiplied by 12. But I know based on that rule that could be square root of 4, and that could be root 12. But here's the trick. Hey, I know what the square root of 4 is. The square root of 4, well, that's just 2. I don't know what the square root of 12 is, so I'm just going to keep writing it there. But bear in mind, because of my rule here, the square root of 48 is equal to the square root of 4 times 12. That is equal to the square root of 4 multiplied by the square root of 12. And I know that the square root of 4 is just 2, so I know that this is equal to 2 root 12. So root 48 is the same as 2 root 12. Wonderful. Let's take a look at this one. Notice that 48 could also be broken down into 16 times 3. So this becomes the square root of 16 multiplied by the square root of 3. Oh, but I know what the square root of 16 is. The square root of 16 is 4. So I can write that as 4 multiplied by the square root of 16, square root of 3 here. And notice when I just write the number in front without any operation there, it's assumed to be multiplication, okay? So there you go. So all three of those representations are exactly the same. This is what we want you to be able to do. So we're going to talk here about converting entire radicals with an index of 2. So we're talking about square roots here to a mixed radical. And here's what you're going to do. You're going to write the radical as the product of two radicals with one of the radicals being a perfect square. Okay, so you have to kind of know what your perfect squares are for this to make sense here, for you to be able to do this efficiently. So then to take the square, then you're going to take the square root of the perfect square and multiply it to the coefficient, leaving the non-perfect square under the radical sign. Okay? Now just note here, if the perfect square, which is factored out, is not the largest perfect square, okay, then the radical is not going to be in simplest form. So you might have to do this procedure a couple of times to get it down to the simplest form here. So just when you look up here, to square root of 48, right here, I took out a perfect square, I took out a 4. But that left me with a root 12 here. Now bear in mind, 12 also has a factor of 4 in it. There was another 4 there. So another way I could have done it was to take the square root of 16 times 3. The square root of 16 is 4. And now notice what I'm left with inside the radical, root 3. Okay, well, root 3 is a small number. It's not going to get any better than that. I'm done. So basically, you're always going to have to check to make sure you're doing this right here. That's what this last little bit is. You're always going to have to check for additional values there. Okay, let's take a look at some examples. All right. Convert the following radicals to mixed radicals in simplest form. So what that means is, bear in mind, it's going to look something like this. I'm going to take the square root of some number a, and I'm going to try to break this down into like b multiplied by the root of c. That's what I want to do. This is my goal. Okay, into a mixed radical form. So root 8. So I got to look at 8 here, and I'm going to try to think, what's the largest perfect square that is a factor of 8 here? Well, I don't have many options here. In fact, I really only had the one that's of any real interest here, and that's going to be 4. So the square root of 8 is going to equal the square root of 4 times 2, which is the square root of 4 times the square root of 2. And I know that root 4 is just 2. So this is going to be 2 multiplied by the square root of 2. 15. Root 15. Convert the following radicals to mixed radicals in simplest form. Okay, root 15. I got to think, what's the largest perfect square that's a factor of 15? Well, my perfect squares are 1, and that's not helpful here at all. 4. Okay, 15 is not divisible by 4. I can't divide that in there. 9. Nope. 16. But 16 is too big. So there was no perfect square that was a factor of 15. So that is my answer right there, root 15. That is as simple as that's going to get. Okay? Root 45. Okay, how can I rewrite this? Well, what's the largest perfect square that's a factor of 45? Okay, let's think about this. My squares are 1, 4, 9, 16, and so on. Well, it's not divisible by 4. But this is divisible by 9. This is the square root of 9 times 5. So the square root of 9 multiplied by the square root of 5. And then I know that the square root of 9 is just 3. So 3 multiplied by the square root of 5. Ooh, root 320. Okay, now this is getting to be a little bit bigger here, so we're going to have to do a little bit more work here. What's the largest perfect square that's a factor of 320? Well, 320 is Well, it's certainly divisible by 4. So maybe that's what we should do here. Let's do this. We'll divide that by 4. And that's going to get me the square root of 4 times 80. And so I know that this will be root 4 times the square root of 80. And I know that the square root of 4 is 2. So 2 root 80. But I look at that number right there, and I think, well, 80, man, 80 is also divisible by 4. Okay, so I've got this 2 here, but I could rewrite this as 4 times 20, and that's going to be 2 multiplied by the square root of 4 multiplied by the square root of 20. And I know that the square root of 4 is 2. So that's 2 times 2 times the square root of 20. So 4 root 20. And now you would think I'm done, but I'm not, because I know that 20 is also divisible by 4. So this is the square root of 4 times 5. So 4 times the square root of 4 times the square root of 5. And I know that the square root of 4 is 2. So this is 4 times 2 times root 5, or finally 8 root 5. Now there is a shortcut you could have taken here. Okay, there is a shortcut. If you had guessed properly what the largest factor, what the largest perfect square was that was a factor of 320, what you would have noticed is that 320, okay, root 320 is also equal to the square root of 64 times 5. And that's going to be root 64 root 5, and I know that the square root of 64 is 8. So I could have gone a lot quicker to 8 root 5. But I'm showing you this here to show that even if you don't choose the quickest route, you can still get there. It's going to take you a little bit of work, but you can get there. 5 root 12. Okay, well, 12 is 4 times 3. And I think that's the best we could do, because the perfect squares less than 12 are going to be 1, 4, and 9. And 12 is not divisible by 9. So 4, I think, is the best we can do here. So this will be 5 root 4 times root 3. And remember, that's 5 times 2. The square root of 4 is 2 times root 3. Or 10 root 3. Now let's take a look at this one. Root 48. So I've got this 1/2 sitting out front here. Okay. Now let's be clever this time. Let's try not to do a whole bunch of work here. 48. I know that 48 is divisible by 4. Totally. Is 48 divisible by 9? No, it's not. Is 48 divisible by 16? Let's just take a quick look here. And yes, it is. And in fact, I suspect that's the biggest one that 48 is divisible by, because when I break that apart here, that becomes 16 times 3, which is kind of a small number here. So I can split that up and make that root 16, 1/2 times the root of 16 times 3. I know that the square root of 16 is 4, so it's going to be 1/2 times 4 times the square root of 3. And notice I can use parentheses here to basically imply the multiplication there. And 1/2 of 4 is 2 multiplied by root 3. And so that's what that radical would look like in simplest form. Okay, Brian and Jeff have been asked to convert root 72 into a mixed radical. So here we go. We're going to take a look at their two different bits of work here and to kind of finish it for them. Brian recognized that the highest perfect square factor of 72 is 36. So he wrote this. Now, we're going to complete his work here. So 72 is going to be root 36 times root. Well, what's 72 divided by 36? 2. And now I know that the square root of 36 is 6. And then there's still this root 2 that's left over that I can't do anything with. So root 72 is the same as 6 root 2. Now, over here, his partner, Jeff, thought that the highest perfect square was 4. So let's complete his work here. So he broke it down into root 4 times root 18. Okay? So now, sorry, I'm just double checking something here. So now we know that the square root of 4 is 2. And then he broke apart root 18, because he knows that root 18 the largest perfect square that's a factor of 18 is 9. So that can be broken down into root 9 times root 2. The square root of 9 is 3. Oh, and then 2 times 3 is just going to be 6. So my coefficient here becomes 6. And that square root of 2 just hangs on at the end, multiplied out. I can't do anything with the square root of 2 because I don't know what the square root of 2 is. And before you go to your calculator and figure out what the decimal is, it's going to be this because it's not a perfect square, it's going to be an irrational number. It's going to go on forever. So whatever number you give me here, it's going to be rounded at some point. This leaves it perfect. But again, just to reiterate here what's going on here, just so that you know, even if you don't know right off the bat what the largest perfect square is, you can still get there just by being diligent to keep looking at that number there and seeing if there's anything else that you can pull out. Is there anything else? And once you get down to a number like 2, well, you're done. All right, convert the following radicals to mixed radicals in simplest form. Okay, root 160. Well, okay, I got to admit here, when I see that, like I'm seeing the 16 in the front here, so I am immediately seeing the square root of 16 times 10, and then I know that this is root 16 times the square root of 10, and that the square root of 16 is just 4. I'm pretty confident that that's it, because when I look at 10, 10 is not divisible by any of the perfect squares. It's not divisible by, well, okay, it's divisible by 1, but that's not helpful. It's not divisible by 4, it's not divisible by 9, and then we're already at numbers that are too big. Okay, let's take a look at 3 root 98. Now, you got to play with 98 a little bit before you see it, I suspect. But 98 is the same as 49 times 2. And 49 is a perfect square. So this is going to be 3 times the square root of 49 times the square root of 2. And I know that the square root of 49 is 7. Now, bear in mind, there's this 3 multiplied out front here. Now, once I've converted that radical into this nice number 7 here, well, now I can do that multiplication because I know what that is. 3 times 7 is just 21. But I've still got that square root of 2 that I really can't do anything with, so it just hangs out at the end there. So 21 root 2. Okay, so this question says, calculate the exact length of the line segment in simplest mixed radical form using the Pythagorean theorem, and then we're going to use the distance formula here. Now, I apologize for a little bit of the mess here. My family has stolen my markers that don't bleed. I don't know where they are, so I'm stuck with this one here. But anyway, when you take a look at this line segment, we're trying to figure out that right here. That's our C. If you look at the triangle that's formed here, okay, this side length is 3, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So by the Pythagorean theorem, that's going to be 3 squared plus 9 squared is going to equal C squared. That's what I'm looking for. Okay, well, 3 squared is going to be 9. 9 squared is 81. So putting those together, that's going to be C squared is equal to 90. And now I'm going to look for the square root. Now, normally when I see something like this, and we talked about this before, normally there would be this plus minus root 90. But when you look at what I'm doing here, that negative doesn't make any sense here. That is contextually doesn't fit. So I know that this is just going to be the positive square root of 90. Okay, now I got to look at 90 and think, okay, what's my largest perfect square that's a factor of 90? Well, I don't know if it's the largest right now, but I can totally see that this is divisible by 9. So this is going to be the square root of 9 times 10. And so that'll be root 9 times root 10, and I know that the square root of 9 is 3. And now I'm done because just like we said before, 10 can't be simplified. So there is no perfect square that's a factor of 10 other than 1. Okay, so that's one way of doing it. The other way of doing it is by using the distance formula. So with the distance formula, we start with the differences in the x-coordinates. Okay, so my x-coordinates here, so that's going to be 3 minus negative 6 squared plus, and then it's going to be the difference of the y-coordinates. Oh, and there should be a square there. Okay. And the y-coordinates are 1 and negative 2. So this will be 1 minus negative 2 squared. All right, now you really got to pay attention to this because it's so easy to get lost in this. 3 minus negative 6 is 9. Now, before someone says, no, it's not, it's negative 3. No. Minus a negative. When you subtract a negative value, you add the 6 there. So this is 3 plus 6. Just like over here, 1 minus negative 2 is going to be 1 plus 2. This ends up being 3 squared. Okay, and now we've already gone through that. We know that this is going to end up being the square root of 90. And we just saw that before. When you break that apart into a mixed radical, you get 3 root 10. All right, now the next little thing that we want to do here is we want to be converting mixed radicals, again with an index of 2, they're looking at just square roots, to entire radicals. And the reason why we restrict it to an index of 2 for the time being is it's very easy to expand on this. We just want to make sure that you get this idea first, and then you can generalize it however you want here. So the first thing we're going to do is we're going to write the coefficient as a radical by raising it to a power of 2, by wherever the index is, okay? And then you're going to multiply the radicals together, and you put them underneath the same radical sign. So a similar process is used for the indices greater than 2. So like just to give you like a symbolic version here, let's say that I had a multiplied by the square root of b. Well, if I want to go from mixed to what we call entire, I want to put that a back inside. Now think about what we've been doing thus far. Thus far, to get something into a mixed radical form, we found something that's a perfect square, and took its root. So I'm going to assume that a is the square root of a number. And in fact, that's easy to do. That's going to be the square root of a squared multiplied by the square root of b. Now notice, I haven't done anything. What's the square root of a squared? A. Because these two basically cancel each other out to get that. Now, so then why would I write it like that? Well, because once I've written it under a square root, well, now I can put those two pieces together. I can multiply them together. Now, if that doesn't make sense right there when I'm using the symbols here, let's go through and take a look at some questions with some numbers, and that should clarify this for you. Okay, so here we go. Let's take a look at some numbers here. So 2 root 5, if I want to write that as an entire radical, first of all, what I'm going to do is I'm going to put 2 under a radical. But remember, I can't change the value. I can't just make this the square root of 2, because that's a very different number here. But I know that 2 is the square root of 4. So this becomes 2 times the square root of 5, which is exactly the same as the question. Now, root 4 times root 5, that's root 4 times 5, or the square root of 20. That's what we're looking for, root 20. Same sort of thing here with 3 root 7. 3 is the square root of 9. And again, when I write it like this, it is exactly the same as this, 3 root 7. Well, this is 3. It's just written in a different form, 3 root 7. But when it's written like this, I can now multiply the two radicands together. Okay, and so this becomes the square root of 63. Negative 5 root 6. Now, okay, here's a trick. Here's a trick. If you square that, now watch, I'm going to do it over here. If you take that and make that the square root of negative 5 squared root 6, that's going to end up becoming 25 root 6. Okay, and now I just want to talk about this. Notice that when you do that, the negative completely disappeared, which means this number here is not the same as this number. You changed it. You got rid of the negative, but there was a negative here. Now it's gone. I can't do that. So when you get a question like this, what you need to do is you need to leave the negative out front. Okay? You need to leave the negative right there. So this becomes the square root of 25 root 6. But with the negative out front. If it's a square root, do not put the negative through. Leave it out front. And then this becomes the negative square root of 25 times 6. And that's the negative square root of 150. And now don't let the fact that there's a fraction there, don't let that throw you off at all. Okay, 2/3 is going to be the square root of, well, 2 squared is 4, 3 squared is 9. Okay, so I just squared the fraction. I just squared the two different parts. I'm writing it as a fraction, but I really did do it separately. Squared the 2, squared the 3. Now, multiply those together. So it's going to be 4/9 multiplied by 18. Okay, well, 4/9 times 18. Bear in mind that you multiply across the top. So 4 times 18, and then 9 times 1. Because really this is like 18 is just 18 over 1. Okay, so 4 times 18 is going to be 72 over 9. Okay, well, hey, 72 divided by 9 is just 8. So this actually, that actually just becomes the square root of 8. Because you do want to simplify what's underneath there if you can. And in this case, that was easy enough to do. Okay, now the next thing we want to look at here is ordering mixed radicals. And this is a very common kind of a question here because we want to know that you can kind of rank them against each other here. So if you've got a set of mixed radicals here and you want to put them in order, probably the easiest way to do that is convert them to entire radicals. Because then all you really got to do is compare the radicands. Okay, the bigger the number underneath the radical, the bigger the square root, or the bigger the root you're going to get here. So let's take a quick look at this example right here. Okay, without using a calculator, we're going to order these. Now, first thing we're going to do is we're going to convert them into an entire radical. So that's going to be the same as 3 squared 9, and then root 5, so it's going to be the square root of 45. 25 is going to be the square root of 25. So put those together. 25 times 3 is going to be 75. So already we can see that this one is bigger than this one. Even though this radical is bigger than this radical, the coefficients balance each other out. This one's bigger here. Root 15, it's already in entire radical form. I'm okay. And this is a small one already. It's smaller than both of these. 6 root 2. 6 is the square root of 36. I didn't give myself any room there. So 36 times 2 is going to be the square root of 72. Ooh, look at that. Those are close. This one's bigger. 2 root 6. 2 is the square root of 4. Root 6. Multiply those together and I get root 24. Okay, so putting these in order, I'm looking at the radicands here. Root 15 is the first. Oh, I'm sorry. We're supposed to put these in order from greatest to smallest. Oopsie daisies. I'm going in the wrong order. Let me cover that up. The largest one here is going to be the square root of 75. So 5 root 3 is our largest one. Our next one is going to be 6 root 2. Okay, so that one's gone, that one's gone. Then 3 root 5, that one's gone. Root 24, whoops, sorry, not root 24, 2 root 6 is one I want to write, gets rid of this one. And then finally that root 15, just hanging out at the end there. And now they're in the correct order from greatest to smallest. Okay, now finally to end off this lesson here, we're just going to take a quick look at how it works with cubes. Okay, so an entire radical of index 3 may be expressed as a mixed radical when the highest perfect cube has been factored out. Now, to do this, you got to know your perfect cubes, and so you've got this little list of perfect cubes over here. Okay, these are probably a bit less well known than the perfect squares here, but just to give you an idea of how this works. So we're going to take the cube root of 40 and break it down. Okay, cube root of 40. Well, 40 can be broken down into, well, I'm helping you out here. There's a 5 there, so this has got to be 8. So now I can take that product and split it into two separate cube roots multiplied together. And I know that the cube root of 8 is 2. So then I can conclude that the cube root of 40 is going to be 2 times the cube root of 5. Now I'm trying really hard, like I did before, to find the largest perfect cube that's a factor of 40. Now, not necessarily the largest perfect cube that's less than 40, Okay, because that would be what, 27. But 27 isn't a factor of 40. Please don't mishear what I'm saying here. I need factors of 40, not just numbers that are less than 40. I see people try to do that a lot here and kind of twist the numbers to make that work here. And now finally here, a mixed radical of index 3 may be expressed as an entire radical by converting the coefficient into a radical and then multiplying by the radicand. So simply going backwards again. But this time what we're going to do is we're going to cube the number to get it in there. So for example, complete the following to convert this into an entire radical. Well, I want to get 4 under a cube root. I got to cube it. So 4 cubed is going to become 64. Okay? And so now this becomes the cube root overall of 64 times 9. And that number right there is going to be 576. So this is equal to the cube root of 576. It's basically the same work. It's just that now, instead of squaring it to get it underneath there, I got to cube it to get it underneath that radical. We did a lot with this particular lesson. I know this is a long one. I hope it makes sense.